Okay, I think I should be recording now. So the last page of this little handout here is an activity for us to go through, an example problem. So one thing that we can take away from what we were doing last time is that when you factor something, here's the example we went over in the last video. When you factor something, uh, the multiplicities of all the individual factors, like here, this 2, and this is a multiplicity 1, and this is a multiplicity 1, you add those together, 2 plus 1 plus 1, they add up to the degree of the polynomial. So all the multiplicities added together give you the degree. That rule should always hold fast. So that means that if you look at something that's in factored form already, like this here, okay, you look at all the different, let's zoom in on that there. You look at all the different factors, like that you see here, like here we have x cubed, and this x minus 1 is to the power 1, and this x plus 2 is to the power 1, and this x minus 3 is to the power 2. Those are the multiplicities of the zeros that we're going to get from those factors, and their multiplicities added together, so 3 plus 1 plus 1 plus 2 should equal the degree. The degree of this polynomial is a 7, a 7th degree polynomial. So that's how that degree works. Now the other thing is, if you were to expand this and multiply it all out, so I mean like going from this format, like a factored format, if you were to go backwards and multiply it all out and put it back into format more like this, okay? If you did that with this example, then you'd have 1x times 1x times 1x times 0.5 x cubed. And that would give you x to the power 7, right? Because you got the 3, the 1, the 1, and the 2. You'd have an x squared from this one because this is going to be squared. So that's where you get the x to the 7th term from. And the only constant multiple that you're going to get there is 0.5. So this number that ends up out here, that's actually corresponding to your leading coefficient. So our leading coefficient here is 0.5. Now, given the information about the leading coefficient, which is that it's positive, and that the degree is odd, we can answer question B based on our chart. So let's go back up and take a look at what our chart was. When we have an odd degree and a positive leading coefficient, we're in this situation. So it means it's going to be going down on the left and up on the right. So we can answer, as x approaches negative infinity, f of x should also be approaching negative infinity. And as x approaches positive infinity, f of x should be approaching positive infinity. So that is the positive leading coefficient odd degree case. Now, what's the y-intercept? The y-intercept, as always, is f of 0, right? The y-intercept is always what you get when you make x equal to 0. So no matter what type of function you're looking at, you can always just do f of 0 to get the y-intercept. So in this case, it's pretty easy. We're going to have 0.5 times 0 for the x cubed, and then 0 minus 1, blah, blah, blah. I'm not even going to bother writing out the rest of this because it's times 0, right? So whatever the rest of this equals doesn't matter, because here, right in the beginning, we can see that we're multiplying by 0. So this whole thing is going to be 0. So that means our y-intercept, in this case, is 0, 0, the origin. Okay. So now let's figure out what the zeros are. The zeros are, the solutions to f of x equals 0 solutions between s. So we get those by looking at the factors that show up here. So just like in the example I did over here, where each of these factors gave us 0, each one produced a single solution, we can do that here. So x cubed, if x cubed equals 0, we're going to have 0 as one of our zeros. Now the multiplicity, because that x factor is cubed, the multiplicity of that 0 would be 3. Each 0 has its own multiplicity. So the next 0 comes from x minus 1. If x minus 1 were 0, x would have to be equal to positive 1. And that is to the power 1, so its multiplicity is 1. X plus 2, if that were 0, x would have to be negative 2. And that's to the power 1, so the multiplicity is 1. And then finally, x minus 3, if that was going to be 0, x would have to be positive 3, and the multiplicity is 2, since that part is squared. So what we can do now is take all of this information together and use this to help us figure out what does the graph of this function look like. Okay, so we know the end behavior is somewhere down on the left and up on the right. We know that's approximately what we have to aim for. We know it has a y-intercept of 0, 0, so we're going to have a point right there at 0. It does also say here that 0 is one of the zeros, the x-intercepts of the function, so that's kind of reiterating the same point. And it's cubic right there, which is interesting. That's going to tell us something about the shape. But let's get the other zeros in first. So I'm going to plot all of my x-intercepts. I have one at 1, and I have one at 3, and I have one at -2, which is over here. So there I've got all the zeros plotted. Now, what I need to do is go through here and fill in the rest of this graph somehow. It's going to be wiggling, wobbling up and down. It has to be a nice, smooth, continuous curve. But I have to pass through each of those zeros in the correct way according to these multiplicities. So at -2, the multiplicity is 1. So I'm just going to pass straight through it. It's going to come from down here. I'm going to shift this over a little bit. And it's going to pass straight through like that. So I put my arrow in the wrong place. I have to get rid of that there. There we go. That's better. It passed straight through because the multiplicity is 1. Then at 0, the multiplicity is 3. So somewhere here, this has to bend over and come down. And when it comes down, it's going to pass through. It's going to pass through in such a way that it levels off first, just like a cubic function. Now then, at 1, the multiplicity is 1. So it's going to pass straight through. Now I'm currently, at this point, I'm now beneath the x-axis. So I have to turn around in some smooth way, and then come back up and go straight through the x-axis at that x-intercept, according to that multiplicity. And then finally, when I get to 3, the multiplicity is 2, which means it's going to have to bounce off. I'm currently up above the x-axis, so I'm going to have to turn around and come back down. But when I come back down, it's going to be like a parabola. It's going to come down, it's going to touch, and then it's going to turn around and head back up. And thankfully, I'm headed in the right direction. After doing all of these things according to my multiplicities, I ended up going the right way, which is good. If you end up accidentally on the wrong side of the x-axis, then you know that you made a mistake somewhere. So that's how, this is a very rough graph, right? I know nothing about the actual y coordinates of these points. I have no idea if this is going up too far or not far enough or anything like that. I don't know exactly where these local maximums and minimums are meant to be, but it doesn't matter. All that we're doing here is getting a rough picture of what the graph is going to look like based on the zeros, the multiplicities, the end behavior, the y-intercept, yeah, that stuff.